Welcome to Math 2318, Section 1.2. Alright, we continue with our look at matrices. In question 1 here, I'm given this matrix. I want to put it in reduced echelon form. So this involves using our row operations. Use this 1 to make 2 zeros under it, and then continuing our way across. Now again, you should do that a little bit just so that you are familiar with the row operations. But sometimes you don't really want to go through the tedium of doing that. So you can go to Wolfram Alpha, or if you have Mathematica, the full version, but Wolfram Alpha is free. And you type in row reduce and then put in your matrix, and again you need the outside set of set brackets to denote the big matrix brackets, and then each of your rows is separated. And so when we do that, what do I notice? Well, I see this situation. I do get an infinite number of solutions because I have this whole row of zeros. I see that x3 is a free variable, and x1 and x2 are writable in terms of that free variable. All right. In question 2, again, I've got a matrix here. We would have to do some trickery because I can't get a 1 easily. If I divide this row by 3, I would end up with fractions. Similarly, if I divide these rows by 9 or 6, I would get ugly fractions. So you really can't get a 1. The strategy, if I were doing this by hand, would be to use the 3 to get rid of the 9. Use the 3 to get rid of the 6. When I say get rid of, I mean make it a 0. And then in the end, divide by 3 once it doesn't matter that we have fractions. But I'm going to use the row reduce again with this matrix to get it in reduced form. So I notice that I've got 2 rows of zeros, which tells me that x2 and x3 are free variables. They can be anything that I like, and that my x1 variable depends upon x2 and x3. So if I go from this back to my x's, and then isolate x1, I get 2/3 x2 minus 8/3 x3. So we get an infinite number of solutions, and they depend upon the values of x2 and x3. In question 3, we have a system, 2 equations, 2 unknowns, but we have h and k in the problem. And so the question is, what happens if we change h and k? How would we get no solution, a unique solution, or many solutions? So in this situation, rather than use row reduce, I want to look fully at how h and k are involved in the process. So I'm going to use this one to get rid of the 5. So I've got minus 5 times row 1. Add that to row 2. Alright, so I'm beginning to see in this process how h and k are involved. Alright, well, let's see. What if h were 2? If h is 2, I've got minus 10 plus 10 is 0. And if k is 20, then I get a 0 here, and I'd have a row of all zeros. Well, if it's a row of all zeros, that means I get an infinite number of solutions. if I have the situation where h is 2, making this a 0, but k is something other than 20, then this piece would turn out not to be 0. And so I've got 0, 0, and something not 0, which means I would get no solution. Now, other than these values of 2 and 20, or 2 and not 20, then I'm free to have h and k whatever we like. So that would occur when h is not 2 and k is any real number. And in our last question, we have some experimental data. I've got a set of points in the plane. So got some points here. And I want to fit these 3 points to a quadratic polynomial. So I don't know which quadratic polynomial is going to fit through these 3 points. So we use our matrix to figure out that. What would the coefficients of A0, A1, and A2 be that would actually fit through these 3 points? So what I want is I want P of 1 to be 10. I want P of 2 to be 12. And I want P of 3 to be 20. Alright, so I put the system into a matrix format. I do row reduce, so I don't have to worry about making all these ones and zeros. And so, well, what do I see here? Well, I see that I do get a unique solution. Alright. A3 is 3, A2 is minus 7, and, A0 is 14, the way we have it labeled, A1 is minus 7, and A2 is 3. And again, that comes from initially how we label these A0, A1, and A2, and their position in the matrix. So here is our quadratic polynomial, which should go through those particular 3 points.